right. Guess people are a little slow joining today. There's only 9 of you so far. So a reminder that we are not going to have class on Thursday because I'm going to be busy with another meeting. But anyway, I'm supposed to give you 2 lectures off for the midterms, evening midterms anyway. So this will be one of them, and I don't know, maybe there will be one later, probably the week of Thanksgiving after your second midterm. I'll probably give you another lecture off. And I believe November 2nd, election day, is also going to be a holiday. I'm not absolutely sure about that, but I saw a notice about that, an email about that a few weeks ago from the Chancellor's office. So that falls on a Tuesday, so that Tuesday, November 2nd, there will not be a class then too. Okay. All right. A few more people have joined. Okay, so let me revisit what we talked about in lecture 15 a little bit, especially since there was an interesting question, a good question actually on Piazza, which maybe not all of you. So, by the way, who asked that question? So Piazza names are anonymous, so I couldn't tell who asked the question, but about the example we did in lecture 15. If you're here today, you can speak up and let me know. Yeah. It was a good question, though. So the question was about the example we did. So here, if you remember, we were looking to minimize this function with these constraints. And then I mentioned that, okay, if you look at the gradient of G1 and G2, it's possible that a gradient of G1 is a scaled version of the gradient of G2. It can happen for some x's. Okay. And so in that case, of course, these gradients will be linearly dependent, and maybe for those x's, if they are feasible, then it could be an issue, because then the analysis that we do, the KKT conditions and so on, are really only for regular x, right? So it could have been a problem. But actually, it turns out in this example, at least, and then the way it could have been a problem is that you may not have been able to identify all the local minima through the KKT conditions, because there could be some points that are not regular that are not covered in the analysis. Okay, but in this example, it turned out actually that all feasible x, even though there could be some x's that are not regular, for which gradient of G1 and gradient of G2 are multiples of each other, you can show that all feasible x's are regular. Okay, and I kind of gave you the argument on Piazza if you looked at it there, but it's not that hard to see. First of all, basically, for this to be a scalar version of this, x1 should be x1, x2, the vector should be some scalar multiple of 3, 1, right? And that scalar multiple should satisfy the constraints, these 2 constraints. And you can easily see that these 2 constraints are not going to be satisfied simultaneously by a multiple of 3, 1. Okay, x1 being something and x2 being something, where x1 is 3 times x2. So if you plug that in, you can easily see that these 2 constraints cannot be satisfied with equality simultaneously. So, which means that only one of these constraints, and it turns out that the second one is the one that's constraining. So, it's this. It doesn't matter. Okay, but so it's only one of the. It doesn't matter which one is constraining, but it's only one of these vectors that will appear anyway. So it won't be an issue unless the unless it's the first one that's constraining, that's met with equality, and and then this gradient happened to be zero. But that can only happen if the vector x is zero. And the vector x being zero, actually, if you plug in zero into these equations, they don't meet the constraint with equality. Okay, so all feasible x are going to be regular for that reason. Okay, so usually you can check this for any problem, and so you don't have to you may not have to worry just because there could be some x's for which these guys are linearly dependent, as long as they're not going to be linearly dependent for all feasible x's. So you're fine. Okay. So in that case, this argument that I gave goes through, and at the end I said, well, since the constraint set is compact, the global minimum is achieved, and we only found one candidate, x star for a local min. We don't have to worry about any others that are not regular, that are feasible. So this is the only candidate a global min is achieved. That's equal to x star. Now, in case you couldn't show that all feasible x's are regular, and so then there may be some possible candidates for local minima that weren't covered in the KKT with the KKT equations. In that case, you might be able to use some other argument to argue that the x star that you found using the KKT conditions is indeed the global minimum. And in this case, actually, since the function is strictly convex and the constraint set is convex and closed, the first order necessary condition is enough for, so every local minimum is going to be a global minimum. And we found one, and that's fine. Finding one is good enough. Okay. Through the second order condition on L. Okay, so that's those are the ways in which you can do it. So so if you're not sure that you found all candidates, or if you're not sure that in this case, if you weren't sure that the candidate for local min that you had was unique, because there could be some others that weren't covered in the analysis because of this regular condition, then you can you might be able to use some other argument to conclude that's a global minimum. Or maybe in some cases the minimum doesn't exist. Global minimum doesn't exist. So all you have is a local minimum. Okay, so that could also happen. So any questions about that? By the way, this whole thing about a regular x, okay, there's a different way to derive necessary and sufficient conditions for optimality that kind of gets around the idea of regularity. Okay, and it's applicable in some interesting situations. Okay, so if you want to read more about that, these are called Fritz-John conditions. Okay, and there's a section in your textbook that talks about that. So you may want to take a look at that. But those are getting into subtleties, which I think is a little bit beyond what I want to cover in this class anyway. Okay, but for those of you who are interested, you can look up the Fritz-John conditions in the textbook. Okay. All right. Okay, so what else did we do last time? So the other thing we looked at was this power allocation problem, right? And we found a way to, we found a solution to this problem using the KKT conditions, okay, and considering all of the constraints in the KKT conditions. So the constraints on the powers being non-negative and the sum of the powers being less than or equal to p. Okay, and we found a nice solution to this problem, which is called the so-called water pouring solution, where the xi's are given by this sum. This is called the water level minus the noise level, and you take the positive part of that. Okay, and you choose that water level 1 over mu to satisfy where is that? Where's the equation for that? Here, this one. So you should choose the water level to satisfy this equation. So the sum constraint is satisfied with equality. And again, we argued that the function was convex, and we found candidate for a local minimum, and so the first order, at least x for which the first order necessary conditions are satisfied, and the convexity will then give us that that's a global minimum. Okay. All right, and yeah, we also could check the regularity condition, like I said last time. Okay, so but then we ended the class with a comment about general sufficiency condition. So in this setup, we have we're trying to minimize f over some, say, x could belong to some constraint set, and in addition to that, you had some equality and inequality constraints. Okay, now this s here, these additional constraints don't have to be there. It could be the real Rn. Okay, but just to keep this problem general, we allowed for this to be some other constraints that may or may not be equality constraint. We'll actually do an example, revisit the power allocation example, where we actually take some of these equality constraints and put it into S because it's more convenient. And remember that if you have all these constraints, then you have a whole bunch of Lagrange multipliers. And sometimes dealing with all of those Lagrange multipliers and looking at different cases might get complicated. Okay, so you could avoid some of the complication by absorbing some of these constraints into S, and if you can deal with that S separately. Okay, so what this theorem tells us is that why is this called a general sufficiency condition? One of the reasons why it's called a general sufficient condition is that it doesn't necessarily involve any second order conditions on the Lagrangian. Right? What this is saying is that if I can find x star, lambda, and mu that satisfy these constraints, right? The feasibility constraints and the complementary slackness constraints for the inequality constraints, then, and if x star is the one that minimizes the Lagrangian function over S. Of course, in order to show that x star is the minimum of this function, maybe you would need to use second order conditions on the Lagrangian. Okay, but there may be situations, and we'll do, as we'll see in the example, we'll just show the power allocation example, you might be able to solve this optimization problem just using first order conditions. Okay, so if you can do that, this could especially happen if S is convex and this Lagrangian happens to be convex in X. Okay, so if you can show this, then X star is a global minimum for P, and it's actually very easy to prove this result, and it's one of your homework problems. I give you the 3 steps, but each of those 3 steps is just basically one line. Okay, but so it's very easy to establish this result, but you can see that this is a slightly more general result than the other sufficiency condition that we gave for local minima, because it doesn't necessarily involve a second order condition. Okay, so, and of course there's also the fact that you can allow for an S which is not necessarily equal to Rn. That's the other slight generalization that we have. Okay, so let's actually see how we can apply this result by revisiting the power allocation problem. So that's today's lecture. Okay. So any questions before we do that, though? Anyone know of a constraint set? Can you describe a constraint set that's not defined by inequalities or equalities? I think it was Chelsea who asked that question last time. It's actually hard to construct such a set. Okay, I gave it some thought. You can construct some trivial examples, but not that interesting. But actually proving that you can't take some arbitrary set that you can imagine in Rn and show that it cannot be written as through inequality or equality constraints is actually non-trivial. Okay, the only, and so actually, which is why most of the time when we talk about constrained optimization, we write it in terms of inequality or equality constraints, because that's how we usually describe sets anyway, right? So, but there are some trivial examples. For example, and think about, say, just an example on the real line, right? Can anyone think of an example on the real line of a set that's not described by equality or inequality constraints?
Or the
Well,
number?
yeah.
I guess the set will just be odd number on the real line. I'm not sure if that's the.
Yeah. So I don't quite get what you said, but think about it, and maybe we can revisit it next week. But there's this very simple example, but it's not that interesting. That's all I could come up with, actually.
How
For
about
something
like
that you can describe
rational
class
numbers?
Yeah.
How about rational numbers, set of?
Yeah. So actually, the yeah, you can think of just discrete points, a union of discrete points, right? That's a good, that'll work. But yeah, think about more generally in terms of continuous sets, maybe that for which cannot be written in terms of inequality constraints or equality constraints. Okay, so that's a good exercise for you guys to do on your own. So let's get back to the power allocation problem. So we have we want to maximize this subject to these constraints, and we saw last time that it's equal. You can equivalently minimize the negative of this too. So to get it to do a minimization framework, also negative log is convex. So this becomes a convex optimization problem. And since the constraints are also convex. By the way, when I say these constraints are convex, okay, if you're not convinced that they are, okay, make sure you can prove it yourself. But we actually showed that if we, in homework 1 or 2, I'm not sure, I think it was homework 1, that if you look at a set that's defined by a convex function being less than equal to something, that's a convex set, right? And it's also closed because of equality. So why is this one a convex set? Because this is xi bigger than something. Why is this a convex set? Anyone?
Because the complement of it is open set.
No, I'm not talking about open or closed. Why is this convex? Xi bigger than 0, equal to 0. We know that this one is like this is a convex function, a linear function that's upper bounded by a constant. This set we proved that it was convex in homework 1. But why is this one? This is going the other way. Why is it still convex?
We proved that a set where the function is bounded above is convex.
It has to be a convex function that's bounded above. So, but now if you take negative xi, that will be bounded above by 0. But is negative xi a convex function?
Yep.
Yeah, because linear functions are both concave and convex. So this is a special case where it works. So even though the inequality is going this way, it's a convex set. Okay, so that's why this whole thing is a convex set. Okay, all right. But when I say that, and when you make a claim like that in an exam, okay, if you're pretty sure that it's correct, you can make the claim. Otherwise, make sure you double check before you make any claims about something being convex. Okay, I saw that in exam 1 already, and people made mistakes. Okay, so let's get back to this. So you want to minimize this function subject to, so instead of, I'll take all these constraints, a whole bunch of them, there's n of them, Okay, and I'll put them all into a constraint set. So I'll just say X belonging to S. And that constraint set is X for which the xi's are positive or non-negative. Right? So this S is a convex set and it's closed. Because again, it's each of the xi's being non-negative is a closed set, which is convex. You take the intersection of closed sets, you get a closed set. You take the intersection of a bunch of convex sets, you get a convex set. So that's why this is both closed and convex. Okay, but then you're left with only one inequality. This guy, right? Just this guy. Okay, so for checking the KKT conditions, or right? So there's only one inequality constraint. Okay, so let's look at the Lagrangian corresponding to that single inequality constraint, because I've absorbed all the other stuff, this S, which I've got to deal with separately, okay, using the general sufficiency condition. So the Lagrangian just involves a function log of 1 plus xi over sigma squared plus mu times the constraint function I equal to 1 to n xi minus p. So if you go back to what we need to check, we just have just the mu, just one mu. So we need to check that it's feasible. So we need to check this, and of course x belongs to S, and then we need to check the complementary slackness conditions. This one for that one constraint, and then we need to make sure that x star minimizes the Lagrangian. So then we can show that x star is global. So that's the approach we're going to take here, right? So so we need to satisfy the constraint, the feasibility. I equal to 1 to n xi star is less than or equal to p. We need mu to be non-negative. We need the complementary slackness, mu times summation I equal to 1 to n xi star minus p equal to 0. And then we need the x star to minimize the Lagrangian over S. So if we do all this, then we prove that x star is a global minimum, actually, it's a sufficient condition for the x star being a global minimum for the original optimization problem. That's what the general sufficiency condition says. Okay, so let's see if we can do this. Okay, so we need to find x star and mu that satisfy the sufficiency conditions. We assume that mu is positive first, okay, and see if that produces the answer, because once we show that these conditions hold, we're done. We don't need to go further. We found the global minimum. Okay, so we can. There are only two cases to consider: mu positive or mu equal to 0. But let's focus on mu positive, because we may have some intuition that that's actually the thing to work with, because we know that this constraint should be satisfied with equality. Because as you increase the powers, okay, you do better in terms of the increasing the bits. Okay, so we'll look at mu being positive and see if this works. Okay, so this function, if you look at this function, this is negative log. Negative log is convex, okay? And this is linear in the x's, that's also convex. So this function is convex in x. Again, if you want to break it down into steps, each of the terms in the summation is convex. And when you sum up convex functions, you get a convex function. We proved that in lecture 3 or something like that. Okay. So, and also this, we already saw that the set S is closed and convex. Okay, so this is a nice problem. Okay, we have a convex function over a closed and convex set. So all we need to do to optimize this function is to make sure that what condition holds, there's a necessary and sufficient condition for this kind of constraint optimization. We learned in lecture 10. We learned that this is the necessary and sufficient condition, that gradient transpose x minus x star should be non-negative for all x belong to S. And this is the condition you, for example, you could have used, some people didn't, in your exam problem for the Moore-Penrose inverse, pseudo inverse, right? So easy. So if you can verify this, then you're done. If you can verify that this transpose x minus x star, whatever solution that you find for all x belonging to S, then you're done. Of course, if you can explicitly find x star using some equations, that's nice. But we saw that in these kinds of constraint optimization problems, it may be easier to kind of use some intuition to guess x star and then verify that that x star is indeed the optimum. Okay, so that's one way to do it, right? Because you could also try and solve this problem separately using Lagrange multipliers, but we want to avoid that. That was not the point of this approach anyway. We want to avoid having to deal with many Lagrange multipliers on these guys. So let's see if we can avoid that. First of all, say x star was an interior point. If x star was an interior point in this minimization problem, we know that the gradient has to be 0. So let's set the gradient to 0 and see what happens, see what kind of answer we get, and then modify that answer to guess a good solution. So let's try that approach. So let's set the gradient equal to 0. Pretend like x star was an interior point. It's not necessarily going to be an interior point, but pretend it is. Then the gradient is easy to compute. So the components of the gradient of L, we did this in the last class. I'll just write it down. It's sigma I squared plus xi star. So that's the ith component of the gradient. We'll set that equal to 0 for I equal to 1 to n. Okay, and if solve this equation, and you get that this is xi star is 1 over mu minus sigma I squared. But of course, for this gradient would be 0 only for interior points, and for interior points in the set, xi cannot be equal to 0, right? So, but this solution xi star would be positive, would not equal 0, only if what condition holds. For this xi star to be positive, 1 over mu must be bigger than sigma I squared. Because if xi star is not positive, then the gradient will not necessarily equal 0. That component of the gradient not necessarily equal 0. So what happens is that we can set xi star equal to 0 in that case, right? So if xi star is 0, that'll happen if 1 over mu is less than sigma I squared. We'll set xi star equal to 0. So this seems like a reasonable solution. And we saw that this was actually the answer we got from the last class. But even without that solution, this seems like a reasonable answer to this problem. That xi star should be the positive part of 1 over mu minus sigma I squared. So it's equal to 1 over mu minus sigma I squared if 1 over mu is greater, strictly greater than sigma I squared. And if it's less than, you just make it equal to 0. Okay, but now, so this is our guess. So this is our guess, right? A good candidate for a possible xi star. Now we have to verify that this candidate satisfies equation 2. Okay, that's not that hard to check. So let's do that. Okay, so first of all, we note that whenever 1 over mu is bigger than sigma I squared, that component of the gradient is equal to 0 because it's that component is in the interior, right? So whenever for all I such that 1 over mu is bigger than sigma I squared, the gradient component is 0. And for all I such that 1 over mu is less than or equal to sigma I squared, we know already that xi star has been set to 0. So if we now look at the gradient, any component of the gradient, so that's mu. Actually, we'll still stick with I such that 1 over mu is less than equal to sigma I squared, and then we'll look at the general gradient in just a minute. Okay, so in this case, we know that this is sigma I squared plus 0, which is greater than equal to 0, right? Because 1 over mu is less than equal to sigma I squared. Mu is bigger than 1 over sigma I squared. Okay, so now let's look at what happens to the entire gradient vector when we take the dot product with x minus x star. So we only have to look at components for which xi star is equal to 0, because for the other components, we know that the gradient is already 0. The partial with respect to those xi's is already 0. So we don't have to include them in the sum when we look at this dot product. So we'll only focus on the i's for which xi star equal to 0, because the other gradient components are already 0 from here. Okay. And then we have to multiply this by xi minus xi star. Okay, but then xi star is 0, so we can simplify this further and just look at, if we look at this, and then xi star is 0, so I'll just have xi there. Sorry. Okay, but if you look at this, we just showed that this guy, whenever xi star is 0, this guy, the gradient is non-negative. So this is non-negative. And this guy, xi, what about xi?
Also non-negative.
Also non-negative, we know that on the set S. So the dot product is also going to be non-negative for all x and S. So we showed the necessary and sufficient condition for x star to minimize L. So this means that L of x star mu is the minimum not quite done yet. So we showed almost everything we need to show. So we've shown, we showed, well, these xi stars, we can make them meet the constraint, and we showed this part, and of course we assume that mu is positive in all the computations. So the thing that remains to be shown is this complementary slackness condition. But we assume that mu is positive so far in this case. So what we really need to show is that there's a way to make this happen with xi star. Remember, the xi star involves a mu. So can we choose a mu such that this happens with equality? Okay. So let's see if we can do that. So we really need to check this complementary slackness condition. But we assume the mu positive, so we need to check that we can make xi star equal to p. But this is not that hard to see, because if you look at this expression here, as I increase mu from 0 to infinity, what happens? As I increase mu from 0 to infinity, when mu is close to 0, the left-hand side is going to be very large, right? Close to infinity, right? Because this is going to dominate sigma I squared, whatever sigma I squared is. So I'll get the sum of these very large numbers, and that'll be very close to infinity. But as I keep increasing mu, then some of these terms in the summation are going to keep dropping out, and eventually all the terms in this summation are going to drop out and I get 0 on the left-hand side. So as mu goes from 0 to infinity, the left-hand side monotonically decreases from infinity to 0. So since it's monotonic, there's actually a unique mu that satisfies, see, this thing with equality. So we're done. Okay. So what we have shown, and that mu is positive, of course. What we've shown is that with xi star equal to this, and mu satisfying this guy with the equality, we satisfy the general sufficiency conditions. Okay, we satisfy this, actually this with equality, mu being non-negative, mu times this being equal to 0, and Lx star as being the minimum of this. So since we have shown all the general sufficiency conditions, this means that x star is a global min Okay. Questions?
Can you reiterate why you would find such a mu?
Why we can find such a mu? Okay, so basically, if you want to solve this thing with equality, right? Right. So you could look at all the possible values that the left hand side can take as mu goes from 0 to infinity, because mu has to be positive, right? And we see that when mu is close to 0, this thing is going to be very large. And as I increase mu, this is going to monotonically decrease. Okay, it can't go up and down; it just has to monotonically decrease. Okay, so as I keep increasing mu, eventually it's going to get to p. When it gets to p, I'll stop, and that's the value of mu t. That satisfies 3, and it's unique. Okay. So everyone see the logic of this? So again, these are kind of tricks you need to use when you apply KKT conditions to solve an optimization problem explicitly, right? So, and these kinds of problems arise in so many different engineering contexts. Okay, and so the KKT theorem is really powerful. Even if it can't give you an explicit solution, okay, you might get necessary conditions that are useful in getting some insights about the solution to the optimization problem. Okay, in the special cases that we do, in class, of course, we actually get explicit solutions, but there are other problems, like you know, when you're trying to solve resource allocation problems more generally in networks, you might be able to use the KKT conditions to derive some insights about the optimal solutions, or narrow down the possible narrow down the search for optimal solutions, and those kinds of insights turn out to be very useful in practice. So actually, this is probably a good time to talk a little bit about the projects. So those of you who have taken the course for 4 credit hours, I'd like you to do kind of a research paper project, and we'll form teams of 3 graduates, 3 students. I guess most of the people taking it for 4 credit hours are graduate students, or maybe all. So you have teams of 3, and then you can choose some research topic that is relevant for whatever research you're working on as graduate students, and see. The goal will be to see how optimization tools are used in your research area, right, or a research area that you're interested in. So that'll be the theme. So, and you can maybe find a paper or 2 on that topic, and then describe that paper in your report. So that'll be the idea. So I'll give you more details about that maybe the end of this week or early next week. But it'll be something that's due at the end of the semester. Okay, there's no final exam, but for those of you who are taking it for 4 hours, that'll be like a final project or something. Okay. All right, so let's take a short break, unless you have other questions, and then we'll do a new topic after the break. Okay. All right, 2 minutes. So any questions about this example or anything else we talked about today. Right. If not, let's move on to the next topic, which is a barrier method. So, we talked about the Lagrange multiplier theorem and the KKT conditions with for inequality constraints, but those are really, you can think about them as analytical techniques to solve optimization problems, right? But how, but suppose you have a complicated problem which you cannot solve analytically, for which you need to use some iterative methods like gradient descent. What do you do? Okay, so there are a couple of approaches. Actually, there are a few approaches to dealing with, because it's an important problem. A few approaches dealing with it, but we'll talk about a couple right now, and then we'll maybe the week after next, when we study duality, I'll mention other ways, other computational methods that are related to duality for solving such problems. Okay, so the first method we're going to study is called the barrier method. Okay, and it applies to problems with purely inequality constraints. So we want to minimize f of x such that x belongs to some set S, and that, by the way, that set S could say correspond to equality constraints, for example. Okay, and then the remaining stuff is, or the set S could just be the entire Euclidean space Rn. And then we have inequality constraints of this form. We'll talk about another method later for dealing with equality constraints. Okay. All right. So S is some closed set. Okay. So why does this work for inequality constraints? That's because what we're going to do is we're going to deal with the inequality constraints through what's called a barrier function. Okay. And a barrier function is continuous, and it goes to infinity if any of the GJs goes to 0. So if any of the GJs goes to 0, the barrier function blows up to infinity. Okay, so why is that? Why might that be useful? What you're doing is that you're going to use the barrier function to replace the current optimization problem, this constraint optimization problem, with something in which these constraints are absorbed into the function being optimized. So I'm going to add something to the f of x that's related to this constraint through this barrier function. And by making the barrier function blow up whenever the constraint goes towards 0, we're going to make sure that when I add that barrier function, I can never get to the boundary of the set, okay, because the function blows up. So I'll always remain in the interior. If I remain in the interior, I can use gradient descent methods, because for any point that's the interior of the constraint set, we know that the first order necessary condition is just that the gradient is 0. And I can find points for which the gradient is 0 by using gradient descent. So that's a high level idea. Okay. In fact, this high level idea is what I'm testing in your computer assignment 2. Okay, where we take a function and add barrier functions to guarantee that the minimum is always going to be in the interior, and then you can just use gradient descent to find the optimum solution. Okay, so you'll see that if you haven't started working on computer assignment 2, you'll see that when you look at it. Okay. All right. So what are examples of functions that will do this? Examples of barrier function. The most commonly used one is called the logarithmic barrier function. And this, you just take the log of the negative of Gj. Okay, so Gj of x is non-negative, is not positive, right? So it's less than or equal to 0. So the log is well defined when Gj is strictly negative, because I'm putting a minus sign in front of it. And of course, what happens to this function when the Gj goes to 0, it blows up to plus infinity. Any of the G's goes to 0. So it satisfies the condition for a barrier function. Another choice for a barrier function, and why are these actually good? There's another reason why these are good choices for barrier functions. We'll get to that in a second. Is just the inverse function. This also blows up. Okay. Of course, these functions are continuous. And the other nice property that these functions have, which you can, I'll make you prove, it's a very short proof, I'll make you prove in the next homework, is that if Gj is convex for all j, then both of these barrier functions are convex in X. Okay, so at least they inherit the convex properties. So if the function f is convex and the barrier function is convex, then the gradient descent applied to these problems will basically converge to a minimum, right? Always converge to a minimum, a global minimum of the problem, right? Not just a local minimum. So that's why this property is important. So how do we use the barrier function? So to use the barrier function, we choose a sequence of epsilons. And these sequence of epsilons is non-increasing, or it's actually strictly decreasing, not just non-increasing. So epsilon k plus 1 is less than epsilon k, and all the epsilons are positive. And also we'll make it go to 0. So there are various ways in which you can do that. Okay. For example, 1 over k is an option, okay, for epsilon. Or you can make it say something faster, like geometric, like 2 to the minus k or something. Okay. So we want epsilon k to monotonically go to 0 as k goes to infinity. Okay, and then what do you do with it? Right. So first we'll see that. Let's define this the feasible set. Remember, the feasible set is the intersection of this set S and all the x's for which the feasibility, the inequality constraints hold. So let's put all this together into one set, which I'll call F. Okay, for feasibility. So feasible set F, script F, is the intersection. It's the intersection of S with the constraints. Now S is closed, and each of these constraint sets is closed, and so the intersection of these guys is going to be a closed set. Okay. All right. So now what we do is use the barrier function in the following way. We're going to minimize over this constraint set F, the function plus, not just the function, but the function plus epsilon k times the barrier function. Let's call this problem pk. Okay, so the original problem without these things, did I give it a name? Maybe I don't know. Yeah, so I should have called this P, I guess. I should call this P. Okay. And this guy is called PK. Okay. Now, since the barrier function goes to infinity on the boundary of f, right? Because basically the boundary, since S intersect with these guys, okay, the boundary of the GJs will also define the boundary of F. Right? And so on the boundary of F, the barrier function is going to infinity. So that means that the solution to this optimization problem, we'll call that xk, must be an interior point. Can't be at the boundary, because at the boundary the function is going off to plus infinity. So xk must be an interior point for this problem. So that implies that what does that imply? For interior points, we know that the first order necessary condition is just that the gradient is 0, but it's a gradient of these two things. Okay, this is good to know, because now I can apply gradient descent, but I have to be careful. I have to make sure I have an initial point that's in the interior of F, and then as you'll see in your computer assignment 2, you can say use a step size selection rule like Armijo's rule, and make sure that your step size is chosen in such a way that you always remain within the set at each time step. Right? So you can do that. You can also do this with Newton's method, by the way, if Newton's method is applicable. Right? And then you can, if you stay in the interior, then hopefully you'll get to a solution where the gradient is 0, the function's convex, and the barrier function's convex. Then you found the solution to the problem. So whatever we studied earlier, iterative methods will work on this this function, because we know that the solution is an interior point. Couldn't do it if the solution could have been on the boundary. And for F, the solution could be on the boundary. Couldn't do it with F, but we can do it when we add this epsilon k times pk. Okay, but then there's a problem. We're not solving the original problem P, but we're solving pk. But the nice thing is I can make this epsilon small. So as epsilon goes to 0, the barrier becomes inconsequential. And we expect xk to approach the minimum of the original problem. Which is P. That's what we expect intuitively, but we have to prove it. So what we can actually show, and that's the result, that's the theoretical result, that every limit point of this sequence xk is actually a global minimum for the original problem. So the practical approach would be to start with a largish value for epsilon, use gradient descent, find a solution, use that as starting point for a smaller epsilon, and so on, and keep going until you've chosen an epsilon. Again, there's a lot of engineering there, so to figure out how small epsilon should be and so on. And then basically at some point you'll get pretty close to a solution to the original problem. Okay, so that's the barrier method. Okay, and the barrier methods are also called interior point methods for that reason, because they allow you to only work with interior points for which your iterative procedures work well. Okay, but those interior points could end up going eventually moving towards or getting very close to a boundary point if the boundary point actually turns out to be a minimum for the original problem. Okay. Right, that's the idea. So let's prove this. It's a pretty short proof, so let's do this quickly. So let's say so let's look at some limit point x bar that was found by, this is the kind of proof we did earlier on in when we looked at you've seen it a few times, right? Looked at say convergence of Army-Hose rule, or even actually for the Lagrange multiplier theorem we use something similar to this, right? So so let's say x bar was the limit of some subsequence of xk, that for which k belongs to some index subsequence index at script k. Okay, so it's a limit point, so it must go to xk, some subsequence of xk must go to x bar, and we'll call that subsequence indices. I'll put that in script k. Now, we know that xk has to belong to f because this minimization problem is over f, right? So xk is a solution and has to belong to f for all k. And f is closed. We saw that already. So if you have a closed set and you take a sequence, okay, then that sequence of points is convergent, say, to x bar in this case, then x bar should also belong to f. That's one of the definitions of closed set, right? So take any sequence inside that set, it has to go to a point within that set. That's for closed sets. The x bar has to belong to f. Okay, that's going to be important for what we say next. Now let's say x star is a global minimum for p, and let's first assume that x star, suppose what happens if x star is an interior, and then we'll talk at the end about what happens when x star might be on the boundary. Okay, but the proof for x star being an interior is a little more straightforward, and then the proof for the boundary point will follow once you have the proof for the interior point. Okay, so let's do it. In the textbook they try to do both together, and it's a little confusing, so it's better to separate it out, I think. So let's say x star is the interior, and f of x star is less than f of x bar. So what this is saying is that x bar is not a global minimum, and then we'll develop a contradiction, because this is a typical way to prove such things, right? So you assume that some statement is true, and then show a contradiction, and then so the opposite is true. So in this case, we are saying that x bar is not a global minimum, and then we'll prove that this can't be the case by establishing a contradiction. So it must be a global minimum. So x bar is not a global minimum means that f of x star is strictly less than f of x bar. Okay, but then let's look at what xk is doing. Xk is minimizing f of xk, f of x plus epsilon b of x. So xk must be f of xk plus epsilon b of xk must be less than or equal to f of x plus epsilon b of x for any x, including x star. Because x star is for some other optimization problem, it's for p, and xk is solving pk, which is a different optimization problem. So xk should be better than x star for the optimization problem pk. Now let's take the limit as k goes to infinity along the subsequence on both sides of this equation. so if I take it on the left-hand side, this guy, because xk is going to x bar and f is continuous, this becomes f of x bar. And so then I'll leave this stuff, the limit of this stuff, I'll just leave it on the left-hand side like that. We'll deal with that in just a second. On the right-hand side, this is not dependent on k, so that just becomes f of x star. But this one, epsilon k, is going to 0, but we have to be careful. What about b of x star? B of x star is assumed to be an interior point, so the barrier has to be finite, right? So the barrier is finite, b of x star is finite. Okay, so since epsilon k is going to 0, this is going to 0, this times a finite quantity is going to go to 0. So on the right-hand side, you have 0 here. Everyone see that?
So why does the epsilon k go to zero again?
Oh, because that's how we constructed epsilon k. So we constructed epsilon k to go to 0 as k goes to infinity in the barrier method.
Okay, thank you.
Okay, so now if x bar is in the interior of f, okay, so we'll consider both cases. Suppose x star was in the interior, but x bar, we don't know where it's going to be. So let's assume that x bar is in the interior of f. Then the barrier function will be finite at x bar, right? Because of the interior. So in that case, if I look at this quantity here, this is finite. This is going to something finite, and this is going to 0. So the product of these two will go to 0. Now, what happens if the x bar is in the boundary of f? Then the barrier function is going to plus infinity on xk, on that sequence, sorry, on that subsequence. Okay, but epsilon is positive and it's going towards 0. Barrier is going to plus infinity, but the product is not going to be negative. We know that for sure, because b cannot go to minus something, it's going to plus infinity. So, and even in this case, this product is non-negative. Epsilon could go to 0 and the barrier could go to infinity in a way that the product is actually still going to 0, but it'll still be non-negative. Okay, so what we've shown is that this guy on the left is going to something that's non-negative. So something non-negative added to f of x bar is still less than f of x bar. That means f of x bar has to be less than f of x star. But then this contradicts what we assumed, that the x bar is not a global optimum. So this means that x bar is a global optimum. So what happens now? Again, this last part is a little bit technical, so I'm not going to go into the details. But you can easily write down the steps once you have the once you have the statement in words. Okay, so suppose x star is not an interior point of f. Then we need to assume that the function is and the function and the constraints are such that there exists an interior point which can be made arbitrarily close to x star. Okay, and then what you do basically is replace x star by that x tilde, and you can get basically in that case what you can show is that you can get arbitrarily close to to the optimal solution through the barrier method. Okay, that's the best you can hope to do.
Does it require the function to be strictly convex near
Could you
X star?
speak up? I can't hear. Let me raise the volume.
Sorry.
Yeah.
Does it require the function to be strictly convex near X star?
No, it doesn't have to be. Just convexity is good enough near X star. So that's one condition, but that's not the only condition for which it holds. So if the function is convex and the constraints are convex, you can show that you can find such an X tilde, okay, explicitly, but that's not the only condition under which you can find that X tilde. So it's not really a serious condition, and it pretty much holds for most examples you'll encounter in practice, that you can find some point that's close to X star. So basically, what this is saying is that if you apply the barrier method, then you're going to get, you can hope to get very close to X star if it's on the boundary, but you can never get to X star. Not quite exactly equal to X star. Okay. All right. So one last comment before we stop today. So interior point methods were originally applied to, barrier methods originally applied to linear programming problems. So this is a linear programming problem. So you're trying to minimize a linear combination of the x's subject to linear inequality constraints. Actually, you can also handle the case with equality constraints, but by looking at what's called the dual. So we'll talk about that maybe 2 weeks from now, okay? But this is a linear programming problem, or an LP. With inequality constraints. Why am I talking about this? In this context, it was when this barrier method was first introduced, and that's why this barrier method is also sometimes called an interior point method. Although interior point methods, there are other ways in which you can guarantee that the solution that you're getting is always going to remain an interior point in every iteration. So, but this barrier method was I guess the first introduction to these kinds of methods, which are generically called the interior point methods. Okay, and the barrier method was introduced in the context of linear programs as an alternative to what was a popular way to solve these linear programs called the simplex method. And the simplex method, what you do is if you look at these linear constraints, they define define a set that's bounded by hyperplanes. Okay, what is that kind of set called?
Polytope.
Polytope. That's right. It's a polytope, and so it turns out that you can show that the solution to these linear programs actually is in the corner of one of these. It's a corner point of the polytope, and so the simplex method is an efficient way to find these corner points. Okay, and so that was the very popular method until the mid 1980s, when a guy called Karmarkar, who an Indian mathematician, showed that barrier-based interior point methods can be much faster, especially for large problems. So linear programming problems, a lot of resource allocation type problems can be posed as linear programs, and they may involve lots of variables, right? So a company trying to optimize how to ship objects to various places to make to efficiently transport things, goods, and so on. You can write those things as large linear programs, and for large linear programs, the simplex method turns out to have high complexity, computational complexity, whereas the barrier method turns out to be much faster. And so that's how they became popular. So if you want to read more about that, there's lots of articles about Karmarkar and his algorithm. Okay, that you can find on the web. All right, so that's all I want to say about the barrier method for now. And of course, once you do the computer assignment, what I said here, that you can easily find these interior points using gradient descent by choosing the step size to stay within the interior. So that'll become much clearer when you actually do it in your computer assignment. Okay. All right. Any questions? We have a couple minutes. Again, a reminder: no class on Thursday. Okay, I'll send an email out to remind you. Oh, I did ask another question by email this morning about your second midterm, because there were a lot of people who wanted to see if I could allow notes to be used, not just one sheet of handwritten notes. There was some technical issues with CBTF, because CBTF didn't give me an option for more than just handwritten notes or books. Because I think part of the problem was is that if I allow you guys to use a tablet or your computer screen to look at the notes, class notes, then it's very hard for the CBTF proctors to keep you from just searching arbitrarily on the web for information, right? Or even posting something on sites which can provide answers to your questions. So that's why I wanted to make it just hard copy notes. But then there was the issue whether everyone could print my class notes to use during the exam. So if everyone can do that, I'm happy with allowing you to use your your handwritten class notes and my notes. If you can print them out, you can use any of that. You can also use the textbook if you have a copy of the textbook, but you shouldn't need it to do the exam. So let me know if you have any issues printing. So some people may not have access to a good printer, and so I don't want that exam to be unfair to them. So that's why I want to make sure that everyone can print before I allow that for the exam. Okay. All right. Any questions?
Oh, can you say what you were thinking about the set that's not expressed as an inequality or equality?
Oh yeah. So the once just take a union of intervals.
Okay, that's what I thought.
Yeah.
It's
not a very interesting set. And even the union of intervals, if you take the union of intervals, it can also be written through inequality constraints if you go to a higher dimensional space. Okay. So if you just take one dimensional space and have a union of intervals, then but add another dimension, then that set you could see just by drawing, you should be able to make it an intersection of two of sets corresponding to inequality constraints. So, but of course, defining the functions to do that may not be easy in all cases. So yeah, if anyone could come up with something that's less trivial than just an intersection of a union of intervals, that'd be great. Actually, you can try unions of two convex sets too, for example, in say 2 dimensions, right? 2 spheres or 2 circles, right? But the problem is, for that, you could still imagine being able to draw some really weird curves that just touch the 2 surfaces and to define the function as being define a function that corresponds to the edge, and then basically the inequality constraint is to one side of that function, and then do the same thing from the other side. So it's hard to construct examples for which you cannot write things. You have to be able to prove that you cannot write it through inequality constraints, and that's the hard part. It's hard to imagine such sets other than trivial things like unions of intervals. Okay, so anyway, so let's not worry about that too much.
I'll let it rest.
Let it rest.
I have another question for if the set S is a constraint set, do we do sort of a gradient projection method? You
could do gradient projection, but you might also be able to just with backtracking. With backtracking, you may not be able to avoid gradient projection, because you basically in say Armyho's rule, you choose in Armyho's rule you're used to choosing your step size so that you always decrease the function, right? Mm. You make sure that you decrease the function, but then you can also choose your epsilon small enough. If you're already in the interior, you can choose your epsilon, the step size, small enough such that you don't go outside the interior. So you can decrease epsilon in such a way that when you start in the interior, since these functions are all continuous, that you will remain in the interior. So that's exactly what you're going to do in computer assignment 2.
Okay, thank you.
So those projection methods are useful, when the optimum solution might be on the boundary, right? But by adding the barrier, you're guaranteeing that the optimum solution is in the interior, and so then you can use backtracking algorithms like Armyho, modify those algorithms so that you always remain in the interior without having to do the projection step explicitly. Yeah, you just keep decreasing the step size. You check, you decrease the step size by a little bit, check to see whether you're in the set or not, and decrease it some more if you're not. Okay.
I have a basic question, like why I didn't figure out like how this is like an iterative method. So now I solve problem PK and
so you solve problem PK for a certain value of epsilon, and actually in your computer assignment, I just make you do it for one value of epsilon. Or actually, I ask you to try it out for other values of epsilon as well, I think. But basically, you start making epsilon smaller and smaller, and see where that solution is going to. So the advantage of starting with a large epsilon is that things will be better conditioned for large epsilon, and then it'll be more in the interior. If the original solution was on the boundary, and there are pictures of this in the textbook if you want to take a look at that. The original solution on the boundary, then by choosing a large epsilon, you're forcing the solution with the barrier thrown in to be more in the interior, so it's be easier for your gradient descent methods to work. and then you start once you have you can use that as a starting point. The solution for a large epsilon you can use as a starting point for your next choice of epsilon, and progressively decrease it until you get something that you think is close to the optimal solution. Again, stopping criteria and stuff like that, those are engineering type decisions.
Okay. I see. Okay, thank you.
All right. Okay, I think we're kind of we're well past out of time. Okay, so see you guys next Tuesday. And the homework is due next Tuesday. There's only 4 problems, but they're a little longish, at least a couple of them.